Welcome to the practice test or a Chapter 4 review. Brief message from our sponsor. I wish they sponsored, but maybe if I mention them enough, they'll send me some pens. These Signo Uniball pens for document camera work, man, they dry fast. Anyway, maybe I'll put that out there each time, and they'll get wind of this and send me some pens for the money. Great pens. Anyway. We're going to find a lot of derivatives on this test. We are not going to use calculator. I'm going to try to specify how I want answers simplified as we're learning. The calculus, not too bad, but some of the derivative work, after we find the derivatives, some of the algebra work may be a little bit tougher than the calculus. So I'm going to try to make it really clear what we're looking for as far as simplification goes on a few of the problems, and others maybe just the derivative will be fine. So let's go ahead and get started. One of the first things we might want to do when we see a square root is think of that as a radical instead of a square root. So think of this as 3x plus 1 to the 1/2. You don't have to do that. Maybe you think very well in radicals, but a lot of people will prefer to use exponents here. So dy dx, I'm going to write y prime here. I always use dy dx on implicit. I'm going to write y prime here. But when I come down for my final answer, I'm going to go, since they asked for dy dx, I'm going to give them what dy dx equals. Okay, so this is clearly a quotient rule. We need low d high minus high d low, derivative of low is 1/2 times the inside function or times the baby function to the negative 1/2 times treat the baby all over the square of the thing below. Good news, when I square the square root of 3x plus 1, I just get 3x plus 1. But things about this that I'm going to want simplified. I'm not going to want negative exponents. Since the problem started as square roots, I'm going to want some square roots. I've got a compound fraction here, so we got some things going on that not entirely crazy about. By the way, this is not times 2. This is times the inside derivative 3. Glad I caught that. So first thing I notice for sure, I can do this. Let's see, 3x plus 1 to the 1/2 times 3. I'm going to put that 3 in front. I've got a plain old 3 times a plain old 3, 9 times the 1/2, excuse me, minus 9/2 x times 3x plus 1 to the negative 1/2, all on 3x plus 1. So things I want to take care of. This 2. If I wanted to get rid of this 2, because we don't want compound fractions, I'm going to multiply top and bottom by 1/2, or excuse me, by 2. So if I multiply top by 2, bottom by 2, I'm going to take my time and do one step at a time. You want to consolidate steps? More power to you. So this 2 in the top has to be multiplied by my first term. So I get 6 times 3x plus 1 raised to the 1/2. 2 times this whole thing is a term. The 2's cancel. That's why I'm doing it. Minus 9x times 3x plus 1 to the negative 1/2, which I'm still not crazy about. All on 2 times the denominator as well. 6x plus 2, or 2 times quantity 3x plus 1. Okay. Now, factoring. Clearly I can factor a 3 out of here. Can't factor an x. What about this 3x plus 1? We're not really used to factoring, dealing with halves and fractionals and negatives. But what if I was just factoring, say, x to the 5th plus 2x squared? I would factor out x squared because that's my smaller number of x's. And I'd get, of course, x squared times x cubed plus 2. I'm going to factor out my smaller number of 3x plus 1s. So my smaller number of 3x plus 1s is 3x plus 1 to the negative 1/2, which is a bit strange. It's just, or new, I should say. So how do I get this x to the third? I took 5 minus the 2 I factored out. If I take 1/2 minus the negative 1/2 I took out, that gives me a full one of these. Take a look. 6 times 3x plus 1 to the first. Look what happens if I distribute this. The 6, of course, survives. 3x plus 1 to the negative 1/2 times 3x plus 1 to the 1. If I add those exponents, there we go, is a half. And then I get minus 9x all on 6x plus 2. Now, that gives me, this can come to the denominator. I'm going to distribute this because I see I can combine some things. I get 18x plus 6 minus 9x all on 3x plus 1 square root times 6x plus 2, which if you wanted to factor a 2 out of that, you could. So I get 9x, 18x minus 9x, 9x plus 6. I can factor a 3 out of that, but there's no 3 to cancel. All on, you could factor the 2 back out, you could leave it. I'd be good with either of those, but I'm going to just write this as, I don't know why I'm putting 6x plus 2 first, just feel like it, times square root of 3x plus 1. Okay. As an option, if you wanted to make this 2 times 3x plus 1, we could actually, I've got a full 3x plus 1 and a half here. We could actually make the denominator be 2 times the square root of 3x plus 1 cubed. You might be able to see how we get that. But anyway, I am good with that for the form for number 1. Okay, number 2, clearly a product rule. Do you want a superfoil? I don't think so, and because it's presented as a product, I want it treated like a product rule. So y prime equals, I want the just plain old first x to the 4th times the derivative of the second, 3 times the baby function raised to the second. Now treat the baby times 4. I would not give full credit for that. If you have, in fact, that's only the beginning of the product rule. But if you have constants as factors, those things should be presented in the front. Let's finish this. First times derivative of second plus derivative of first, 4x cubed times just plain second, 4x minus 5 cubed. So we end up here with, let's see if anything good happens. I get a 12x to the 4th times 4x minus 5 squared plus 4x cubed times 4x minus 5 cubed. And this is kind of a mismatch kind of deal here. I've got this thing written in factors, so should I FOIL this out and then distribute, or superfoil this, distribute, or should I maybe, since we got some factors, try to factor? I think it's presented as factors. Let's try to answer as factors. dy dx. If I factor out, I can factor a 4 out of these. I can factor 3x's out of these. I can factor a pair of 4x minus 5's here. And what am I left with? If I factor a 4 out, I've got a 3. I've still got an x here. I don't have any 4x minus 5's. Over here I've got no 4x cubes, but I've got a pair of 4x minus 5's. Any payoff in foiling this? 4x cubed times 4x, not anything there, minus 5 squared. Here I get 3x plus, if I FOIL this, I get 16x squared minus 20 minus 20 minus 40x and plus 25. So there was a little payoff there. I get 16x squared minus 37x and a plus 25 times these guys. So we start seeing, well, yeah, there's a little payoff there. But then if we're going to factor, should we talk about maybe factoring that? Maybe that factors. At some point, you know, we ought to be in a position where pretty reasonable response to this, and I believe this is a good response. You would lose points if you left See, this 3 and 4 should definitely be the lead of this. This 4 should be the lead of that term. So I'm going to dy dx. I could put this since I worked through it, but I'm in good shape here. Just trying to show a point that, you know, is this more simplified? I don't know. It's kind of nice to see that I've got these factors here. Kind of nice to see I've got those terms. 12x to the 4th times 4x minus 5 squared plus 4x cubed times 4x minus 5 cubed. Maybe you just want to take it to this point. Okay. So that gets us through the first page. Let's look at number 3. dy dx. Y prime equals, outside function is 2 something to the, or excuse me, is 1 something to the second, so 2 times 1, 2, the something stays the same. I'm going to write this as sine of 5x cubed rather than in this form, and the reason is it really helps me see the chain rule that's going on here. I've got a 5x inside of a sine inside of a cube, so we got some definite chain rule stuff left to do when we take the derivative of the baby. So times the derivative of 1 is 0. The derivative of something to the third is 3. That thing to the second times, now I need that inside derivative. Derivative sine of 5x, well, the outside function is sine, outside derivative is cosine of 5x, and now times its inside derivative 5. So let's clean that up. I've got a factor, a factor, a factor, a factor, a factor, and a factor. I have constants, 2 times 3, 6 times 5, 30. I've got a 1 plus, I'm going to write this as sine cubed 5x. I've already used the 3. I've got a sine squared 5x, and I've got a cosine 5x. So dy dx, keep that in mind so you don't get pinned like I do. Might have to write small on some of these, or maybe draw to a conclusion there. Put your final answer down there. That would be fine. Get careful here. Let's read the directions. We're in derivative mode right now, but take a look. We want second derivative. And I'm going to expect you're going to know the trigonometric derivatives. The inverse trigonometric derivatives, I'm going to give you those when we have those, but this you're going to need to know. So y prime is cotangent's derivative is negative cosecant of, in this case, x on 3, treat the baby times 1/3, and we might write that as negative 1/3 cosecant, that's squared, I think I said squared, but it is squared, x on cubed, which I might want to think of as negative 1/3 cosecant x on 3, all of it squared. So here's dy dx. And we could write it this way, but I want it this way for the next derivative. So let's see, y double prime. You're going to hear me say it, you already have a lot. If we have a constant times a function, the constant survives derivation. So it's just negative 1/3 times. You don't have to put the parenthesis there if you don't want to. It never hurts though. So this is I need the derivative of the outside function. That is 2 cosecant x on 3 to the first. And now I need the derivative of cosecant x. So the derivative of cosecant is negative cosecant, in this case, x on 3 times cotangent, this is the times here, x on 3 times the derivative of x on 3, 1/3. So we got a lot going on here. Let's see, factor, 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 factor. I can multiply in any order. I've got a negative times a negative positive. I've got a 1/3 times 2, 2/3 times 1/3, 2/9. I've got a cosecant x on 3 times a cosecant x on 3. I've already taken care of that negative. Cosecant squared x on 3, and I've got a cotangent x on 3. So dy dx is either 2/9 times that, or you can make it 2 and put it all on 9. I'm just going to make it 2/9. 2/9 cosecant squared x on 3 times, cotangent, ignore, x on 3. Okay, this one, better be alert to this, because we have rules for instance, cosine of a difference. And the nice thing is this is going to turn into sine when I take the derivative. So I'm going to take the derivative just as it is, and I get y prime equals, this would be the negative sine of my inside function, pi on 3 minus 4t times the inside derivative. Derivative of pi on 3 is a constant, 0. Derivative of that is 0. Derivative of negative 4 on t is negative 4. So that is positive 4 sine of pi on 3 minus 4t. And we think, well, that's really good. Well, this one we're going to simplify. And in this case, I have sine of a difference. And the rule for sine of a difference, for instance, if I have sine of A minus B, is that can be written as sine of A cosine B minus sine of B cosine A. And why would I do that here? Well, because sine of pi on 3 and cosine of pi on 3 are known values. We can simplify. So I get 4 times sine of pi on 3 times cosine 4t minus sine of 4t times cosine pi on 3, or if I draw a pi on 3 angle, 60 degrees, 1, 2, root 3. I get 4 times sine of pi on 3, y on r, root 3 on 2 times cosine 4t minus sine of 4t times cosine pi on 2, x on r, 1 on 2. If I distribute the 4 through this, that's encouraging. Understand, this 1/2 is not times that 4t. This 1/2 could be out in front. Distribute the 4 through this, I get 2 root 3 cosine 4t minus 4 times 1/2, 2 sine of 4t dy. Oh, and look at, are they still t's? Good. Dy dt equals. Okay, moving on. This is organizational here. Good problems. Just got to make sure we organize these well. We're given f and g of 2, and we're given f derivative, g's derivative at 2, also at 3. We're going to have to make sure we pay attention to these guys. I want the derivative of f of x times g of x. That's not an open circle, that's not of, that's f of x times g of x. So I need the derivative of a product, and that would be the just plain function at 3 times the derivative of the second, g prime of 3, plus f's derivative, f prime of 3, times plain old g. And now, take your time looking up to the chart. Everybody in this class has shown they know how to do this, but many have shown they know how to also mess it up. So I need plain old f, when x is 3, f of 3 is 3. I'm going to find g prime of 3 is 5, plus I'm going to find f prime of 3 is 2, and I'm going to find plain old g of 3 is negative 4. If you have any repeat values here, 3, 5, 2, negative 4, if any of those repeat, they better repeat up here as well. I should have all of these guys involved. So I get 15 plus negative 8, or 7. Okay. And now I have f of g. This is a function inside of a function. I want the outside derivative. Leave the baby alone. then treat the baby. But I want that as x is 2. So I want f prime of plain old g of 2. Plain old g of 2, I think I can fit everything on here. Plain old g of 2 is 2 times g's derivative at 2 is negative 2. And f's derivative at 2, f's derivative at 2 is 1/3. So I get 1/3 times negative 2, or negative 2/3. Easy, and easy to mess up as well. Okay, let's work through this. I'm going to treat this like it's all just to the 1/2. So my derivative becomes 1/2 times f squared x plus g squared x to the negative 1/2 times the inside derivative. And the inside derivative would be, follow this, 2 times, leave f of x alone to the first, right, times, see this could really be written as f of x squared. So it's 2 times f of x to the first times, I still have to use f's derivative. Plus likewise g, my outside function is squaring, so 2, leave the inside function g of x alone to the first times g's derivative. But I want those derivatives at 2. You could have put 2 in here to begin with. I should have. So I'm going to be really careful. I know that I need to find my f of 2. Plain old f of 2 is 7. So this becomes 1/2 times 7 squared. Now, f, I already found out, f is 7, so this guy is 7. Maybe I'll just go right down the line one at a time. Let's back up on that. So now I need g of 2. Plain old g of 2 is 2. So I get 2, but it still has to be squared, to the negative 1/2, times 2. Plain old f, as we said, f of 2 is 7, times f's derivative at 2. F's derivative at 2 is 1/3. Plus 2 times g of 2. Plain old g of 2. Well, g of 2 was 2. Times g's derivative at 2. G's derivative at 2 is negative 2. Okay, again, this is no calculator test, so we got to battle through this. 1/2. This is 49 plus 8, or 49 plus 4, excuse me. This is 53 to the negative 1/2. We're going to have to deal with that. I get times, let's see, I get 14/3, plus times minus, minus 2 times 2 times 2, 8. This is 8, or minus 24/3. So I get 1/2 times 53 to the negative 1/2 times negative 10 on 3. All multiplied. So what's going to stay in the numerator? The 1 is, the negative 10 is, for negative 10. In the denominator, I've got a 2 times 3, 6. Shouldn't have written it there because I'm going to simplify that. In the denominator, we started with square roots, end with square roots. I've got a square root 53 for a final answer of negative 5 on, when I divide by 2, 3 root 53. Yes, that would be a deduction. We need to have that. So quite a bit of organizing, and you know how the test goes. You're going to have a problem that looks virtually identical to this. Okay. Implicit differentiation. This should almost be a welcome problem for us here. Find lines that are tangent and normal to the curve at the given point. So we need a slope. I already know this. I already know my tangent line could be written y minus 3 equals something times x minus 2. The only way that won't be the case is if I end up with something undefined for the slope. And then it's either going to be y equals or x equals. And my normal line can also be y minus 3 equals something times x minus 2. I want to look for the slope at 2, 3. So I need to differentiate, and clearly that is implicit differentiation. 2x. Clearly this is a product rule. So a lot of that missed on the quiz. I know it's a little looking thing, but it's still a function times a function. So it's plus the first function x times derivative of second. The derivative of y is dy dx. It's not y dy dx. It's just dy dx. You can use y prime here, but I would be careful with it. So product rule, that's first times derivative of second, plus derivative of first 1 times second, minus derivative of y squared with respect to x is 2y dy dx. That's the chain rule portion of it, the inside derivative, derivative of y. And the derivative of 1 is not 1, it is 0. I'm going to group my dy dx's, x dy dx minus 2y dy dx equals subtract 2x, subtract y. Oh, I haven't divided yet. And now I'm going to factor out dy dx. When I factor out dy dx, I'm left with the other factor of x minus 2y. I'm going to divide that away. Now, if I was going to simplify this, anytime I have a preponderance, that's a good word, of negatives, I might multiply by negative 1 on negative 1. If I was just finding dy dx, I would say this is a better answer. 2x plus y on, I'd get a positive 2y and a minus x. Did I do that right? 2x plus y, I'd have a minus x and a plus 2y. But bottom line, once I get to this point, I can go ahead and substitute in 2, 3 because we're really looking for these. But I'm going to substitute 2, 3 in here. So I'm going to call it f prime of 2, 3, carefully substituting. I put 2 in for x, plus I put 3 in for y, on 3 in for y, 2 in for x, and I get 4 and 3, 7, 6 minus 2, 4. There's my slope at that point. So my tangent line is 7/4, and my normal line is negative 4/7. Okay, not too bad. Implicit differentiation. Sometimes these second derivatives can become a challenge. First derivative, no problem for us. This is derivative x squared plus, wrong, some problem. 2x plus 2y dy dx, that's the chain rule, equals 0. So, see if we follow this, dy dx equals, I would subtract 2x, I would divide 2y, and I get negative x on y. That is dy dx. And now I have to find the second derivative of that. So if that's dy dx, then d2y dx squared, or the second derivative of y with respect to x squared, is low d high minus high. So that's minus, that negative is up top there. Otherwise I could put it out in front of the whole fraction. I'm going to treat it up top here. Minus high negative x, d low dy dx, all on the square of the thing below. But I don't want dy dx there. But dy dx is this guy that can go there. So let's see how that works out. I don't think I'm going to come up here. So I've got negative y, I've got plus x times negative x on y, all on y squared, and that's great, but I do not want complex fractions anywhere in this on this test. So I would multiply by y on y, and I get negative y squared minus, this is plus times minus minus x squared, the y's cancel, that's why we do it, all over y to the third. So dy dx, negative x on y, d2y on dx2 dx squared is negative y squared minus x squared all on y cubed, and don't you dare reduce y's. This is a term. Okay, I think I'm going to do one more problem here and then pause at that point. And the only reason is because we kind of shift gears when we hit number 10. So I think I'm going to go through number 9. Find the points on the curve where the tangent is parallel to the x-axis. If it's parallel to the x-axis, the tangent line, that means the tangent line has a slope of 0. So I want to find the slope formula, set it equal to 0. That's going to be my starter. So slope formula, implicit. I get 2x plus, there's my product rule again, first x times derivative of second dy dx, plus same old derivative of first 1 times plain old second y, plus now I'm taking the derivative of this, 2y dy dx equals 0. Has kind of a familiar feel to it. So I get dy dx times, I'll show this one a little bit different way, x plus 2y, group my dy dx's factor, subtract everything else to the other side, negative 2x minus y. Or dy dx equals negative 2x minus y on negative x minus 2y. Oh, no, that's divided by x plus 2y. Now, how could this be different? They could ask for, what if it was parallel to the y-axis? Okay, a fraction would be parallel to the x-axis, slope is 0, but a fraction is 0 when the numerator equals 0. So when negative 2x minus y equals 0. If they ask parallel to the y-axis, that's when the slope is undefined, and the slope is undefined when the denominator is equal to 0. So I'd set x plus 2y equal to 0. But in this case, I can simplify this, add y to both sides. I get y equals negative 2x. Now, that is not my solution. That is the equation of the tangent line where it's parallel. But that intersects this. So now I can take negative 2x and I can substitute it in for y, and I have equation just on x. So we've got a lot going on this problem. This one will be worth a few more points than some of the others. So that becomes x squared plus x times negative 2x plus all of negative 2x squared equals 4. Looks bad, it's going to get good in just a second. Here I get x squared minus 2x squareds, and this will ultimately be plus 4x squareds equals 4. That's 5x squareds minus 2x squareds, 3x squareds. Let's solve for x. I get x equals, I divide 3, I take the plus or minus square root of, find the points. You should expect more than 1. So that is plus or minus 2 on root 3, or maybe better, plus or minus 2 root 3 on 3. Which means I have a point where the slope is parallel at 2 root 3 on 3 something, and I have another point at negative 2 root 3 on 3 something. And I can find those y coordinates by taking these values and putting it in here for x and solve for y. But I can also find them by putting them in here. I think I'm going to choose here, because that's the intersection of these two curves. So I can use this curve. So times 2, this would be negative 4 root 3 on 3. Times negative 2, this would be positive 4 root 3 on 3. So a lot going on that one. Again, going to be a little bit more weighted than some of the other problems. And look for the second video when we start talking about some inverse trig functions here. Thanks for joining in. Signo, Uniball, buy it now.